Alright, I'm making a video as a response video to a Sean Carroll podcast with Roger Penrose. I've never cared for any Roger Penrose quote I've ever heard. I've found kind of obnoxious. So anyway, I thought I would at least try to play some of this. Maybe I'll speed it up a notch just so I don't go totally insane. Yeah, this might be a very long video, or we might just give up. We'll see how it goes and such. So I think we might need a little more volume.
Important and interesting.
Okay, so I gotta back up a little. Start fair and increase the volume just a hair. Oh, I love this transparency thing. Beautiful, so pretty.
Hello, everyone, and welcome to the Mindscape Podcast. I'm
It might be a little too loud. Okay, right there maybe.
your host, Sean Carroll. I don't want to mess around a lot at the very beginning of this one because you've probably heard of today's guest, who is Sir Roger Penrose, one of the most important and interesting thinkers and scientists of recent years, of my lifetime, that's for sure. If you don't know Sir Roger Penrose as a physicist, you might know him as a writer of popular level books, The Road to Reality, The Emperor's New Mind, and so forth, but he made his bones, as it were, in the field of general relativity, Einstein's theory of gravity. Along with Stephen Hawking, he helped invent the singularity theorem, the idea that if you get enough stuff in a region of space, general relativity says you can't help but collapsing to a point of infinite space-time curvature. But Roger Penrose has done many other things in addition to that. Just as one example, early on in the podcast, he mentions doing some early work on the nature of infinity in space-time, and what he's really referring to is the idea of a Penrose diagram, which general relativists use to make a little picture of an...
I don't know what that little glitchy stuff is, but anyway, it doesn't probably make any difference. So we're already, it's just all this woo, space-time as improperly metaphored and described and visualized, and connecting it to our minds. Somehow the brain is space-timing. Woo, there's a singularity collapsing. Woo.
space-time. Roughly speaking, Penrose diagrams are as important for people in general relativity as Feynman diagrams are for people doing particle physics. And not only that, Roger Penrose has come up with the Penrose triangle, the Penrose process for extracting energy from black holes, Penrose tilings, twistor theory, the cosmic censorship hypothesis, many other extraordinarily influential ideas in general relativity. And he doesn't stop there with
So the good thing is he didn't say anything like useful ideas. Just nonsense. All theoretical rubbish. Make somebody a sir for that. No, don't do that. It's a bad idea. I gotta come up with a better way to turn the video on and off. That didn't work.
relativity. As you do know, if you're a fan of Penrose, he's been working in recent years with ideas in quantum mechanics. He has his own, basically, idea about how wave functions collapse in quantum theory, and the implications of those ideas for consciousness, and how that relates to Gödel's theorem, and artificial intelligence, and all these big picture ideas. Now, in my mind, the thing about Roger Penrose is that he understands four-dimensional curved space-time better than any person alive. So that's what I chose to talk about in our conversation, mostly in this particular podcast. We do go on to other things. We talk about consciousness and quantum mechanics for the last half an hour or so. We could have talked about those for hours more, but we both had schedules to meet. Sorry about that. One thing I got to note is that we both got stuck on the names of the three people who were the authors on the papers on black hole, the laws of black hole mechanics. It's Jim Bardeen, whose name we forgot. Sorry, Jim, who wrote papers with Stephen Hawking and Brandon Carter about that topic. Now, talking to Roger
How exciting. So this is really just going to be just it's not even a conversation. It'd be more, I bet I could get a more rational conversation if I, drove to the Vatican and listened to a couple of cardinals talking back and forth about their rubbishy religion. Like, oh no, I think Jesus was trying, and he didn't really know God loved him. He just kind of thought a little bit he did, but he was a little uncertain. Does God love me? Does God hate me? Am I measuring up? Does God think I'm a shitty son? I mean, he had some angst about his, you could see that conversation will likely be infinitely, okay, you just the word first, infinitely more reasonable than this silly conversation they're going to have. That's how bad, and they're doing science. This is going to be a science show. Woo! Woo! Yeah, it's just woo. Oh.
great thing about him is he's fearless. He has enormously creative, deep ideas. Many of them have been incredibly successful and influential. Many of them are idiosyncratic. Many of them I don't agree with. I didn't agree with his ideas about entropy back when I was first learning cosmology. I later realized he was completely correct in his picture of entropy in the early universe, and that had a huge impact on my career. So I'm always happy and respectful talking to Roger Penrose, whether or not I agree with his ideas. You can decide whether or not you agree or disagree with any of them in particular. What the point of the podcast is to give you information about...
Yeah, what a pussy. No, the point of the podcast is just do this pretentious pussy bullshit. So you say, I might not agree with some of his ideas, and you talked about how brave he was, and yet you're such a coward that you won't even point out that, no, I think he's full of, he's out of his mind, talking this rubbish about collapsing singularities and shit. No, you didn't even have the guts to say it. Gutless crap.
Are, you're the one who's got to make the decision about what to think at the end of the day. So this was an extremely fun conversation. It's a great way to start off the year 2019. Let me just do two quick podcast announcements, of course. You can always support Mindscape on either Patreon or just directly through PayPal. Go to the webpage to find it.
Yes, and if you don't like that, I'll just throw 2 commercials at the beginning. There was actually 2. I have to skip the ads. I haven't seen that before. We have to skip the ad twice. Oh, that was charming as fuck. I love science. Science is so much fun. Oh, scientists. Yeah. Oh, I need my 48 cents. I mean, this 48 cents is really important to Sean Carroll. He needs this 48 cents.
And like any podcaster, we love getting good reviews on iTunes and elsewhere. So we have a wonderful list of guests coming up for the rest of 2019, but I can't think of a better place to start it off than talking with Sir Roger Penrose about the nature of space-time, black holes, and cosmology. So let's go. Roger Penrose, welcome to the Mindscape podcast.
Hello, great pleasure.
Now, you've not only done a lot of amazingly important scientific intellectual work, but on an amazing variety of topics. And so usually for the podcast, often for the podcast, I like to focus in on one. I have the feeling that my people will be upset if we don't hit all of the various high points of, cosmology.
The audio is a little bit different, so I have lowered it a hair. I think it might be okay, but I can't find out, really. Yeah, really, I can't. I could pause this thing and then switch the things, but that's probably more work. So never mind.
Quantum mechanics, consciousness. So we can spend 3 hours if you want. But I'm going to try to get the main things in there. But I thought starting with space-time would be a good thing to do. I mean, this is where you sort of made your bones early on. Is it safe to say the first big thing you published, the first major result, was the singularity theorem for black holes?
I think that's true. I'm trying to remember the order of which things were done. I had 2 Phys Rev Letter articles, and one was on conformal infinity, how one represents radiation, gravitational radiation, by squashing infinity down.
So, squashing infinity down. So he got a paper published squashing infinity down. See, this is the bullshit, right? They can publish almost any kind of drivel, and I can't even post a comment on a message board. Too outrageous. What, you have a mechanical theory? Oh, no, we can't have any of that. There's certainly not enough woo in your theory. Oh, God. Oh, okay, I have to turn it on again. Continuing.
A place where you can see it, more or less. And this is a nice way of talking about things like gravitational radiation, electromagnetic radiation, and so on. But then I wrote this up.
So anyway, he really is getting old. I remember this guy way back and all that kind of stuff when I was growing up. So I mean, I've always disliked his crap. Reason to hate Britain. But anyway, continuing.
In 1965, originally 64, I think, which was about black holes, except we didn't call them then at that time. This was gravitational collapse. Going way back to work done by Chandrasekhar in the 1930s, when he was on the boat coming to England, still I think 19 or something, I can't remember, and he worked out that a white dwarf star would have a certain maximum mass, and if it was more than that, then it would collapse basically.
Right, Chandrasekhar living.
Yeah, whatever, this nonsense of this collapsing thing. None of these little holes have been anywhere near anything ever. They've never done anything. If one of them hit something like the Earth, it should create some kind of great catastrophe thingy. We don't see any of that in the universe. The only thing we see in the universe are supernovas now and then. So all of this is just, obviously this collapse ends up with an explosion. You can't destroy the energy. There is no singularity nonsense. You can make dense objects, but as soon as the density gets too great, you're doomed to collapse because you have too much pressure on the inside and there's not enough pressure on the outside to contain it. We live in a vessel. The universe is pressure. We're pressurized. We're in compressed oxygen tanks. There's no, I'll make you a little bit smaller and you'll become super compressed solid pressure or something. No, that never happens. It's just mush. Mush, mush, mush. Compressed mush.
So Chandrasekhar was what was worked out at that time. The white dwarf stars being very, very concentrated, so that the mass of the sun might be concentrated in something like the size of the Earth. But these stars are certainly known, the companion of Sirius and other such stars. So it was these are things that were well established. But what Chandrasekhar showed was if the mass was above a certain amount, which was a bit more than the mass of the sun, 1.5 times the mass of the sun, then there was nothing would hold it apart, and it would collapse down. And the question is, what happens to it? And Chandra was very sort of...
So this is just so funny. There would be nothing to hold it up when it. The point is that the pressure. See, their theory is so backward. They think things are pulling. The atoms are, every little bit in the universe has got little pull, vacuum cleaners, and it's sucking up space and pull. Everything's pulling towards each other. It's an obvious, stupid place to start. It's a dumb premise. The first premise should be, yes, the air is thinner than water. You shouldn't start with the idea, what if water's thinner than the air? I mean, it's just that backward. Ugh. Yeah, this is just so bad.
About this, and we're less speculating on what happens. Whereas Eddington at the time was thinking, this is ridiculous, that can't happen.
Chandrasekhar got a lot of pushback, right, for this idea that there would be gravitational collapse.
Yes, indeed. He got into a lot of trouble. Because, it's a wild idea, so I'm not surprised, actually.
Yeah, you should get a little pushback.
Yes. But, of course, that didn't get down to a black hole. He just said one is left speculating. I suppose he had some sort of idea that it might.
Speculating about stuff you have no business speculating about. It's so distant from any kind of facts or evidence that it's almost like, why are you even asking the question? Because anybody can answer it with any kind of horseshit. You could make, you can create gremlins, you can create angels, you can create flying rhinoceroses, you can create calculating frogs. You can make up any kind of bullshit story because there's absolutely no way to say, oh yeah, well here's the picture and it doesn't match the picture. We have no pictures. Zero. It's just all made up crap.
A lot of early work, which people say there was this. I forget people's names. I'm right on this road at the moment. Anyway,
this happened with age. What was my mother's name? Mommy? Yes, that's it. Mommy. Mommy said.
Early work where people wondered what happened to very massive objects, but until general relativity came along, there wasn't.
In my pants with those very massive objects. On her chest.
Which was problematic. And it was in 1939 when Oppenheimer, of atom bomb fame, and a student of his, Snyder, and they worked out an exact model, according to Einstein's general theory of relativity, of a collapsing dust cloud. And it was a picture of a black hole that we have now.
Oh, just such a pile of crap. Einstein's whatever, his nothing formula. I mean, really, realistically, it's just a description of the inverse square law. And then he screws up the passage of time just to make a mess out of it. I mean, if you would have just left it alone as the inverse square law, all right, then you wouldn't have to worry about any of this black hole crap. But it's the fact that he bent time, which bent the velocity, which bends the momentum, which bends everything, that's where everything gets broken. Anyway, I'll
But a
show.
lot of people were a bit suspicious of whether that was really what you'd expect because, well, there were two things. One is the dust cloud was material that had no pressure, and so it wouldn't push itself apart at all, and it would fall into the middle, and it wouldn't stop itself from pressure. The other point was the model was exactly spherically symmetrical, it's exactly the same all the way around, and so that the matter, as it collapsed inwards, would be aimed right at the central point. And so the fact that you got infinite density there was not perhaps surprising, and people thought, well, maybe if it was irregular, it would fall in and maybe swish around a bit and then come swirling out.
Right. So they thought this was an artifact. This was maybe some special.
All right, so infinite density. I mean, it's just because, see, their model, when they bend the space thing, they're not admitting it's a, they don't have a mechanism. They're not accounting for energy. So they can contrive an infinite amount of it. So by using the vacuum cleaner model, see, you can basically just say, my vacuum cleaner, I can just keep turning the valve up, keep turning the motor speed up infinitely. See, there's no rule that told them ahead of time there's only so much stuff you can suck in. So they have this infinite sucking power. And that's where all the math goes to hell, is because they've contrived a mechanism that couldn't theoretically possibly exist, which is an infinite amount of space being sucked by an infinite motor of infinite power. Where if you have an external pressure, you sort of understand that the cosmic background radiation, only so much energy. The whole universe, the photons coming from the universe, only so much energy. So there's a limit to how much pressure there is if you have some mechanical theory that's rational. But if you can do this pull thing, there's no... You can't just logically say, well, you can only pull this fast. They're basically saying the little homunculus inside of the electron can pull as fast as he wants to, as fast as he has to. It's unlimited. He has unlimited pulling capacity. So that's where their math goes to hell. That's where this whole thing turns into nonsense. Is because they've just created a source of infinite energy, and they should know better. I mean, hell, they should know better. Oh, we really shouldn't be doing that. Whoops.
Usually what you'd expect.
That's right. Well, I think there was argument about it. Now, I know John Wheeler was very worried about these things, and the worry came particularly to a head when Martin Schmidt, a Dutch astronomer, well, Dutch-American astronomer, and he concluded that this was the first quasar. And he noticed that the signals from this object, first of all, they were redshifted, so that meant probably it was receding from us at a very great speed. And secondly, it was extremely bright. And thirdly, it had variations in its brightness of the order of a week or so, which suggested that it couldn't be much bigger than the solar system. And therefore, you had this huge amount of energy coming out, which is something like more than the whole galaxy. And it was a real problem. And the picture which was presented was that you had something which was down at the kind of level that
So 1 minute ago it was made out of a collapsing star that was 1.5 masses of our sun, and now a whole galaxy is coming out of it. Oh, okay, that's really smooth continuity there.
Schneider model would say you have a horizon at a certain point, and this would be where this energy would be released at that sort of scale.
Sorry, this point about the variability is an important one. It's sort of not obvious to people, but it's a very simple, fun argument, right? I mean, if something varies rapidly, then it's probably not any bigger than it takes light to travel across the object, right?
Exactly,
and so,
right, yes.
weak time-scales, that's the size of the solar system, which is small by massive extragalactic object standards.
That's right, yes. So it was a great puzzle, and I know Wheeler was very worried about this, and he talked to me about it, and he said, well, look, this means we've got something down at what's called the Schwarzschild radius. This was a very early solution of Einstein's equation. It's called the Schwarzschild solution, and Schwarzschild discovered it soon after general relativity. And unfortunately, he died not long after that. But it was the first solution of what could represent the body. He was thinking more in terms of a star or something, where there was something inside which was matter, and the equations changed when you get into the matter, and so that there was no singularity there.
Yes. So anyway, I can't say exactly what they're... Again, this is just where they're allowing the speed of light to somehow decide some sort of event progression, and therefore all this shenanigans can happen because, at these scales you can make light traveling great distances, and now you can make almost anything happen because you have an infinite amount of time inside of the delay and then you apply the stupid illogic of the bent space-time nonsense and apply it to a photon, and all of a sudden now the photon never moves, even though it's going the speed of light. So you end up with an infinite amount of time also somehow curled into this stupid singularity or into this event horizon. Ends up being timeless. So it takes you forever to fall into the black hole. La 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 la.
If you imagine squashing the matter down to this radius, which is called the Schwarzschild radius, then you get into a very curious situation, which was described by the Oppenheimer-Snyder collapse model.
And then so they took a long time, right, decades, for people to really appreciate what the Schwarzschild solution was trying to tell them all along. That is just a tricky little general relativity question.
That's right. Well, usually people thought there was a body inside, and so you did explore what happened when you extended the solution inwards. And it was the first clear, I think the Oppenheimer-Snyder model, just before the Second World War, was the first clear model of what could be happening.
Right. And then the quasars that you mentioned, I mean, so there's this bright object in the sky very far away.
Yes.
Right. Now we know these quasars are just galaxies, immature galaxies. And the quasars have more energy than the galaxies today, so they're smaller and have more energy. And so to me that kind of screams logically that galaxies are expanding, not contracting, and that's why the stuff on the outside of the galaxy is moving too fast, because guess what? It's leaving the galaxy. Of course it's moving faster than our mathematical models would indicate, because it's not orbiting a galaxy, it's leaving the galaxy. Jeez.
Seemingly, this could be a candidate for an ultra-compact object that might be what we now call a black hole. So is it really accurate to say that experimental data nudged theorists towards trying to understand this better?
Oh, absolutely true, yes. It certainly nudged me to thinking about this.
Yeah.
I thought about the Schwarzschild horizon and so on, and didn't think much of it as a thing that might be out there. Usually one thought that if you squash the Earth down or the Sun down to that size, it would be pretty unrealistic.
Right.
But if the thing is big enough and it collapses itself inwards, and I should say that the Schwarzschild horizon, the size of it, the diameter of it, is proportional to the mass of the object. So that if the object is much, much bigger, then the volume, which goes as the mass cubed, is something which the density wouldn't be so necessarily very large.
And what is the Schwarzschild radius for the Earth? I feel like it's very small number.
It's tiny. I forget what it is. Something like a centimeter.
Centimeters or something like that. Yeah,
exactly,
like
yes.
a neutron star with the mass of the Earth would be the size of Los Angeles or something.
Something like that.
Black
yes.
hole's a centimeter
Yes,
across.
yes,
So that's a lot of mass in a very tiny area.
Oh, absolutely. Yes. But you see, I know Wheeler was very worried about this. He said, "What happens? Do you get the singularity, or does it swish around and come out again?" And it was a big question. Should you trust the Oppenheimer model? Oppenheimer-Snyder model?
So at least somebody figured out the obvious. Well, wouldn't that be creating an awful lot of pressure on the inside? And wouldn't that pressure tend to want to get to the outside? And what would be stopping it from getting to the outside? Oh, the pressure that's in the outside? Somewhere there has to be a limit again. Like I said, they just created an infinite well. There's no other way to say it, right? By not creating a force on the outside that's pushing in. So that would always be limited. There's going to be so much pressure. They created this well idea, and the well just doesn't have a bottom. They just never said there's any place we have to end, because we have an infinite supply of energy, because we're doing virtual energy. None of this has to be accounted for, because it all goes into some other dimension. It all goes to a place where it never gets out, so they don't have to account for it. Which is just cheating. Cheaters. Oh, I have to turn it back on. Oh. I hate to do it, but I will.
Unrealistic because of irregularities. And at that time, I should say the quasars was around about 1962, I think. And around about that time, there was an argument by two Russians, Lifshitz and Kolotnikov, and they had produced a paper which seemed to say that singularities did not happen in general circumstances.
Right.
So that when the thing collapsed, if it was a general, irregular, collapsing body, it would swish around, it wouldn't reach these infinite densities, infinite curvatures, it would swish around and maybe come swirling out again or something like that. So that's the picture that a lot of people had.
But you were able to prove otherwise, and what I love about it is, in some sense, and maybe this is exaggerating because I don't know the history very well, but in some sense, what you did represented a shift in technique in general relativity from finding exact solutions that were simple to making an absolutely general statement that just relied on the sort of intuitive powers of the theory, but made very rigorously
No,
mathematical.
you're absolutely right. It's just, you see, either people had found models which required a lot of ingenuity, but they usually had some special symmetry or something like that. And these solutions, very beautiful solutions often, but whether they were realistic, well, they were all very special.
Right.
The only other way you could was to use high-power computers and work out. But then in those days, we didn't have the kind of computers we have now,
Right.
and it was pretty hard to get any impression as to what happened in the general case. So I started thinking about this. I'd been thinking about other problems a little bit like this. One of them, which I never published anywhere, was worrying about the old steady-state model.
Okay.
See, this was a cosmological model that was sort of in vogue when I was becoming a graduate student and becoming interested in general relativity in a serious way. And in Cambridge, where I was, it was a popular
It was
view.
a hotbed, yeah.
Yes, that the universe, although it was expanding, and the mass sort of got less and less by the expansion, the mass was replenished by hydrogen gas appearing spontaneously. And it was
Appearing spontaneously. I love it. Yes, that's just great physics. Let's have some more of that spontaneous talk. That's exactly what physicists do. They walk around and go, up, spontaneous, at least, theoretically. On some scale of the universe, that event was just spontaneous because, on some scale it's in a frame where the photons never move in a billion years, and so when it happened here, it was spontaneous because the movement is so slow. It's infinitely slow, which means it's infinitely fast somewhere else. But I mean, what? A physicist who says spontaneous. Yes, the concept is perfectly rational. We don't need to have none of this going across any. Who cares a Schwarzkopf radius? We don't need any of that shit because we can just spontaneous go from here and just pop in over here. We'll just disappear here and poof over there. And then if you can do that, well, why don't you just poof out of nothing? Why don't you just spontaneous instead? I mean, I'm just saying, anybody who's done a little bit of physics, the word spontaneous, just like the word random, they ought to be trigger words. Like, oh no, they've been playing with that bullshit. Those words do not do. It's like one of that Catholic conversation. They just never will say the word like evolve or something because it's just not it's a bad word in religious sense. Determinism. Oh no. Can't even use that kind of word. I mean, to use spontaneous, I mean, it's just a word that any physicist should know. Well, infinity is a word they shouldn't even touch. Just so bad.
beautiful model in a way, because as the expansion took place, the matter was replenished, and you had a universe which was sort of stable and it remained forever in this way. It had some curious properties, but the question that I was interested in is, could you in any way make this consistent with Einstein's general relativity without having to introduce negative energies and things like that? And you could see pretty well that that couldn't be the case if it was very symmetrical. But then I started wondering, well, look, suppose it's irregular in some, quite serious way. Does this still cause a problem with general relativity? And I came to the conclusion, using sort of topological types of arguments, that you couldn't save it.
Is it even possible to give us, I know this is a very intricate differential topology question, but is it possible to give a flavor of the argument? It's something like gravity is always attractive, right? I mean, that's the basic principle.
That certainly, but it was mainly how it behaved on light rays. That was the real argument. You look at how light rays behave, and it's a bit like a lamp.
Okay, so isn't this hilarious? Attractive light rays. Okay, so at least they got this stupid, you heard him say it, right? Oh, it's fundamentally attractive, when no, it's fundamentally pushing. It's fundamentally repulsive. Okay, things are pushed into each other. The earth doesn't love the sun. It's just the truth. Okay? They're being forced. It's an arranged marriage. There is no love in the universe. It's all hate. Everything is being thrown out of somebody else's window. Nothing is going into somebody else's house saying, I want to live with you. No, they're being kicked out of somebody else's house. but really the attractive photon. So we're back to the virtual photon with the magic powers. The thing, the cannonball hits you and it makes you fly towards the cannon. It's the anti-cannonball.
You have a parallel beam of light rays, and the way that mass acts on that is to it focuses like a positive lens, so a convex lens, would cause this parallel rays to focus. Now, if you have this astigmatic lens, suppose you imagine a lens which in both one direction it's positive and the other direction it's negative. I mean, you don't normally find these lenses, but that's the way gravitation behaves. So if you just go through empty space, then it focuses one way in one direction and expands out in the other direction.
And this is what leads to spaghettification if you fall into the black hole.
Yes,
right?
it squashes you one way and stretches you in the other. Exactly, that's right. So that's what empty space curvature does. But the thing is, if you have combinations of lenses, it's quite interesting. You can do this just with ordinary optics. You have lenses, and you put them on an optical bench. And if you had these astigmatic lenses, what you find is that if you suppose you had one and another sitting right next to it, an astigmatic lens which is at right angles. So I mean, they're both the planes are parallel, but the direction of the image is at right angles. Then one cancels out the other, and so it's just like a flat piece of glass. But now suppose you pull them apart. Then you find there's a residual effect, which is a focusing effect. And this is connected with the energy in gravitational waves. So the gravity acts like an astigmatic lens. But when you have a lot of them one after the other, there's a net effect which is focusing, as though there was matter. And this is the effect that gravitational energy has, is focusing. So I knew about these things by thinking about these focusing effects and so on. And it was using this kind of argument, together with topological arguments, that you could see if you reached a point of no return, and that was a critical point is knowing what that meant.
Right. So all just made up rubbish. Just nothing. Just not even like the blue tinge on my fingers. That's how much evidence they have. You know, the amount of blue compared to the rest of me. It's a tiny little, just a smear of indication of something. And they go on this whole wild, let's go find Little Red Riding Hood hunt. Ugh.
You would find that this focusing property would be irreversible, and you could show that there had to be some singular.
Just nonsense. This focusing capacity. This all that rubbish he's talking about. Blah blah blah. It's all just rubbish. It doesn't even have a mechanics. They can't draw a picture of any of this crap. Again, if they try to draw a picture of Einstein's gravity in 3 dimensions, it'll look just like a bunch of rays going into the sun and the earth. Just rays. It'll look exactly the opposite. A bunch of, like the light bulb has the little rays coming out. It'll look just like that with the rays going in. That's why they don't draw you a picture. It's because it looks like, say in Susskind, just to avoid having to say convergence, he says it's an anti-divergence. You know, because the rays diverge as they're going out. So he calls it an anti-divergence, so he can avoid having to say it's a convergence and imply that there's an external pressure. I mean, this is just such crap. Oh, it's just pathetic that people fall for this crap.
Inside the object that was collapsing. Really, it gets to a point where you don't know what happens. It sort of stops. Space-time gives up.
But singular doesn't just mean special. It means the curvature is getting infinitely big in some sense.
That's the expectation.
Yeah.
Although the argument that I had didn't directly show that. It just showed that there's something stopping. Space-time comes to an end and it stops.
Right.
And the normal expectation is that it gets, these focusing effects become infinite, and so things just crumple up and you can't get any further.
And you don't necessarily, it doesn't immediately follow logically that it's a black hole, right? But you had ideas about that.
Yes, that's true. But the argument that I had didn't prove it's what we call a black hole. It just showed that you had the singularity. You had to make a further assumption, which is what I call cosmic censorship, which is if the singularities in general are of the kind that you roughly speaking can't see them, then you do get what we now call a black hole. But it did depend on this cosmic censorship hypothesis.
Right. Which is still not completely proven, is that correct?
I think that's correct, yes. There's a lot of evidence that it's true, I think, in general. Well, the argument is that it has to be.
Amazing. Yeah. Oh, we've proven this, right? Oh, yes, of course. I believed it and you believed it. Isn't that what the definition of proof is? I fell for it, you fall for it, and he fell for it. There, we have proven it, established it as a proof, and you wouldn't believe it if it wasn't believable, would you? Of course not. You're not an idiot. You're not a sucker or a noob or a doob or any of that, fall for anything kind of. You wouldn't be buying one of those bridges, would you? Oh, you might put crappy ads, 45-cent ads on your videos, but you're not that big a moron. Fuck.
General situations that you can cook up special examples which disagree with it, but they're not realistic.
So the astronomers, with their data, prodded you to think about this problem, and then
Absolutely,
you
yes.
proved something. Did your proof prod the astronomers to take black holes more seriously?
It did eventually. It was quite interesting because you could see somehow a huge amount of skepticism about black holes. And I used to be asked to give lectures at these Texas symposia, which happened every year at first. And usually I was asked to give a talk, something about black holes. And you could see gradually people beginning to take it seriously, and more people. There's a whoop that sort of went over to the other side. Right. It sort of happened very rapidly once enough people got used to the idea.
And then, I mean, on the theoretical side, black holes became a whole area of study, and Stephen Hawking and Brandon Carter and other people.
Yes, indeed. Yes, that's right. And Hawking's remarkable results about the fact that they do a very tiny amount of radiation. And so if you imagine in the very remote future of the universe, then these huge black holes, well, you see, now we see huge ones. Initially, they were just the odd double star system where you see one star and the other one, it seemed to be going around something else that you couldn't see,
right.
But maybe there was some plane where material was coming out of it. You couldn't see the object itself. And so people speculated that was a black hole. The evidence was pretty indirect for a while. But now the evidence is, well, indirect in a sense that you don't actually see directly into the hole, but you see things like in our galaxy. We have a what we call a supermassive black hole, which is about 4 million times the mass of the sun. And it's really remarkable. You can see these pictures. So you have to speed up a little bit,
yeah.
But not that much. And you can see stars going around in these sort of elliptical orbits, and there's nothing in the middle.
Yeah, they're going around a big heavy thing that you can't see. So,
yes, that's right.
Except it's not that big. It's a small, compact, heavy thing you can't see.
That's right. It's pretty small by the. Yeah, that's right. A 4 million solar mass. I'm not sure quite how big that is, but it's not huge.
It's less than a light year, right? Yeah,
yes,
it's very tiny. But so when Hawking, circa 1974, argued that black holes are not completely black,
yes.
if you take quantum...
Are you still listening? What the hell? Oh, this is just so fascinating, isn't it? Just riveting.
into account, they
That's
radiate. How did that strike you? I mean, was that controversial at the time?
I can tell you exactly what happened. You see, I think I was away from Cambridge. So I was working in Cambridge at the time. No. This wasn't. No, when was this? That was
74, early 70s.
I must have been in Oxford by then. Oh.
But you and Hawking had become close and were
Yes, no, I knew him well.
Yeah.
But the point was, I'd come back from somewhere. Exactly where, I can't remember, I haven't worked that out. But Dennis Sharma, you see, who was a great friend of mine, and I learned a lot of cosmology from, and he was Stephen Hawking's supervisor. And Dennis was a great person for getting the right people to meet each other and so on, people who might benefit from encounters with other people. And he knew all the physics that was going around, so I learned an awful lot of physics from Dennis. But anyway, I come back, and Dennis told me, have you heard the latest? Stephen Hawking has showed that black holes radiate, you see. And I said, what? So I phoned him up, you see. I phoned up Stephen. And I said, what's this all about, you see? And he said, well, it's tied in with the ideas about thermodynamics and how I said that makes a lot of sense. So no, it didn't take me long to come to the conclusion that it was probably right.
Well, to be fair to the audience, you had previously shown that you could extract some energy from a rotating black hole, but a limited amount, and you had to do it sort of intentionally. It wouldn't be automatic, but that kind of pushed people on the road to think about these questions.
Yes, that's right, because you could get stuff out in a sense. You could get energy out of it. But this was going a little further. It was curious because, I must have been in Oxford, because I remember how this came about. We used to have these meetings every Friday in my office in Oxford with my graduate students, postdocs, and people interested. And if somebody was visiting, we'd have them to give a nice little talk. And Stephen was visiting at the time. And he was telling us he was imagining little black holes which might be created in the Big Bang. And the idea was, if they were rotating, would they lose their energy in the rotation? And he showed some calculation about this. And it was actually not very long after that, you see. I must have been visiting, I can't remember exactly how it was. I saw Dennis at that point. But I phoned Stephen up.
Oh, I love this. I phoned Stephen, and his computer answered and said, he's on the potty right now. You'll have to come back later. Yes. Yes, well, I know it's not much of a personal story, but yes, well, it was on the party. There's nothing I can say. It's on the party. I couldn't talk to Stephen because it was on the party. Just happens that way. Oh, where were we?
Following up on this calculation he'd done previously about the rotating ones. And I think that he found that they didn't need to be rotating, which rather surprised him.
Does it, right?
Yes, that's right.
And I think that in the famous textbook by Kip Thorne and also Misner and Wheeler, there's this picture of an advanced civilization that has built an energy extraction device around the supermassive black hole at the center of their galaxy. There's a lot of energy we could, in principle, get out.
Absolutely.
We'd be free from our dependence on foreign oil sources if we could really harness black holes this way.
Well, you see, this was the argument. I wrote a paper in the Italian journal. There was a conference in Italy somewhere, I forget where now. And there were people talking about very massive stars and so on. And I was asked to give a talk on black holes, which I did. But I'd come to this conclusion that you could extract energy. And I imagined that you could do this by having particles which would split up into two and so on. But when it came to the talk,
I realized I might look like a total fool if I start talking about this free energy crap by lassoing, electrons from their attractiveness and breaking up their family so they all have divorces and stuff, and a bunch of extra electrons fly out because they no longer love each other anymore, so they're a bunch of rejected and ejected and kind of depressed electrons with little tiny wieners. And I've this whole theory that the tiny wienered electrons were going to be collectible. I thought, well, maybe somebody's going to say you're a fucking lunatic. yeah maybe you were afraid of that, maybe. Sir, like I said, they knighted him. Oh, the inverted penis electron. Yes, let's give you a Nobel Prize for that one. Great theory. That explains everything.
Which way around was it? I think I did get it that way around. But I thought also about the civilizations rotating around the hole and extracting energy out. And there's a simple argument. You can see they could do this from general principles. They just lower, fill buckets full of rubbish and lower them into the hole and tip the rubbish in, and they would extract more energy from the masses of the rubbish. So
and when Hawking did explain that black holes give off radiation, this all came as part of this, as you mentioned, thermodynamics.
Yes,
This package that black holes have entropy.
Yes.
And there was this sort of analogy between what black holes do and the laws of thermodynamics, and this really said it's not an analogy, it's true.
All right. So, now they have black holes hurling through space at half the speed of light. That somehow, right, by some unknown gravitational theory, this is impossible. I'm just letting you know, like even a high school kid could probably figure out the math that says this would be impossible for two black holes to come from some location in space and actually miss each other. See what the consequence of gravity is this: if you're coming from a distance, it bends you right into each other and you collide. You don't miss each other. Can't really happen. Yet they have a whole LIGO-y thing built on these false, phony, fake, mathematically impossible premises. Because they just made all this shit up. It's all just such crap.
Have entropy.
Well, it was curious because, you see, the entropy of the black hole, it was really Bekenstein had a
Mechansteinical. It's all Mechansteinical, the entropy. I mean, they have this idiotic notion that the black hole ages. So it creates this preposterous pressure, this preposterous amount of pressure, and everything's locked together. And somehow, though, over time, something happens to, I'm getting old. I'm an old black hole, and I'm starting to... What a pile of crap.
Rough argument, but I was quite happy with that because it seemed to be very consistent that the area of the black hole should have an entropy, and that Bekenstein's argument was pretty convincing to me. But Stephen then had a much more exact argument, and which was more impressive mathematically. But this came after a lot of discussions between Stephen and Brandon Carter and who's the other one?
I know the paper you're talking about is the laws of black hole mechanics, but I'll tell the audience afterwards.
There may be, I think there were 3 people doing it before.
Yeah.
But they were exploring the analogy between thermodynamics and black holes. But Stephen definitely just thought it was an analogy. I remember talking to him about this, and I was sort of thinking it was real, you see. Mm-hmm. But you see, in a way, he'd been looking more deeply into it than I had, because he realized if it was really thermodynamic, then the black holes had to have a temperature. And that
we all know
didn't seem to
that's
be the
not
case.
true.
Yeah, of course, they just swallow things. There's no way it can have a temperature, you see.
Right.
But then he found that they did.
I mean, I think that in A Brief History of Time, he mentioned that he was literally annoyed at Bekenstein for suggesting that the entropy was real, and that motivated him to do this.
That's interesting. I hadn't quite realised it was that argument, but that's right.
Did that help get you interested in entropy? Because it was just a few years after that that you started talking about the entropy of the early universe.
It must have done. I'd have to try and put it together. But to be able to assign value to this entropy, that was crucial for that, you see. I can't quite remember the order of my thinking here, but certainly something which I played around with a lot was thinking about, well, I thought about it in the steady state model, you see, and the issue of entropy balance troubled me, you see. But there, you see, you had this creation of the hydrogen, which the fact that it was condensed, you see, in form objects, could be a source of the entropy, and so a source of low entropy, I should say, a reservoir of low entropy. So that's how it sort of squared itself in my mind with the second law issue. I've been worrying about it then already. But when that had to be given up and one was looking at models which expanded and didn't have creation of matter, at some point, I was worrying about this question, but it didn't really have substance to it until the Hawking entropy, well, Bekenstein-Hawking entropy value for black holes and how huge it was.
Yeah, so just, I need to be very fair to all of the audience listeners. Entropy, they've heard the word before, but it's roughly speaking a measure of how random disorganized a certain system is.
Sure.
And in some sense, intuitively, you might have thought that a black hole has zero entropy. It's not a lot of different ways a black hole can be, right? It's not like a cup of coffee where there's a lot of arrangements of the atoms inside. But Hawking and Bekenstein show that it's actually a huge number. And that inspired you in some sense to start writing about the second law of the thermodynamics says that entropy tends to increase in closed systems, and therefore it's not surprising that entropy used to be lower in the past. Okay. But cosmologists have a long history of being confused about this issue.
Yes.
All right, so, blah, blah, blah. See, look, the idea is that the energy can't be destroyed, and all you're really talking about is how can it be trapped. So the idea of entropy breaks down when you make traps. So the whole universe would just be the same level of temperature, the same, and that's all entropy is. It's just a way of measuring temperature, and you're just saying that there's more temperature when things get stuck close to each other, and there's less temperature when they're further apart. So we're just talking about proximity. So when you have locations that have stuff that's within an inch of each other, and there's locations where it's a foot from each other, the average would be something in between the things that are a foot apart and the stuff that are an inch apart, and that would be the native state. And entropy is either closer together or further apart. Now, they don't really understand that the real entropy of the universe is because there's an external pressure pushing everything together. So that's why they can't come up with a rational theory of entropy, because they don't understand where most of the energy in the universe is, which is in the form of gravity. Whatever.
Let's just be honest that this is the most profound, and it's been quite a profound effect that you had on my career, because it was your papers emphasizing this problem of why the early universe had such a low entropy, which I thought were completely convincing, and puzzled by why my fellow cosmologists don't take this seriously. So yes. Why don't you explain how you think about it?
No, you were one of the few people who really latched onto it immediately. But I was just as puzzled why people didn't take it seriously. But the basic argument is this, as you say, I mean, the entropy, or the randomness, if you like, increases with time, and that's the second law. Another way of saying exactly the same thing is you go back in time, it decreases. So as you go back and back and back in time, you should find the entropy very small. Now, what's the earliest evidence that we directly see of the universe's state? That's the cosmic microwave background. So this is radiation coming from all directions, electromagnetic radiation. And this radiation has a lot of entropy in it, but the main point that I'm going to sort of concentrate on here is if you look at
I love that he said it. Okay, the cosmic background radiation has entropy in it, which is energy, and just the idea of it. So a couple of times he sort of indicated that, yeah, the universe really looks like a bunch of external energy. He did sort of say that a little bit before. So there's they just can't. They're this close to getting it right, and they still miss. Still can't land on the target.
The curve which represents the intensity for different frequencies. See, we have this thing, the curve goes up and then comes down again. And it's what's called a Planck curve.
The amount of light at different wavelengths.
That's right. So there's a certain temperature where it's maximum, and then the radiation at high frequencies it goes down. And this Planck curve is observed, the Kobe satellite, when it went up. You have to tell me the dates, I don't remember.
1991, 92, yeah.
Okay. The Kobe satellite measured this curve of the intensity for different frequencies of this radiation. They found an extremely good fit, almost perfect fit to the Planck spectrum. What does the Planck spectrum tell us? It tells us what we're looking at is maximum entropy. I mean, that's the whole point of it. It's what they call the black body radiation, which meant maximum entropy. So here, this is what I call the mammoth in the room.
Yeah, so now they're just using jargon, right? They're just now replacing frequency with wavelength with period. They're saying the same things. It's pressure. Yeah. But, we'll just use some other silly word to call it. They'll call it, maximum entropy.
You go back and back in time where the entropy is supposed to be going down and down and down until it reaches a maximum, which is sort of the wrong way around. and I don't know why people didn't worry about that more. But the point is, the answer, I think partly because it's muddled up with the expansion of the universe.
Look, you can look it's kind of easy to understand. When all the little bits are way far apart, the universe is frozen, right? When they're all smashed together, it's like the most hottest place you could imagine. Hell. Yeah, that's all it is. That's all entropy is. It's the transition from one state to another state. But there's nothing else it can do except pressurize or unpressurize. There is no other option.
Well, some think, the universe is expanding, and so maybe there's not much room for entropy down there, or something like that.
I think it's partly that, and partly that when we're taught thermodynamics, gravity is not a part of it, right? We
Yes,
don't think about
I think
black
that's
holes and so
right.
forth.
Yes. I mean, there were people like Tolman, one of the early mathematical physicists who studied cosmology, and he understood pretty well about the entropy issue. So people certainly did understand it, the right people at that time. But anyway, yeah, you've got this huge amount of entropy in the radiation, which is a lot actually. And then why is there's that second low hole when it starts off at the top and it's got nowhere to go, if you like. And you could have to convince yourself that the expansion of the universe doesn't help,
Right.
which is the point Tolman did understand. But the other issue, you see, you've got this radiation coming from all directions in which it has this thermal character. But the other point about it is it's also very uniform, so it's almost completely uniform over the whole sky. If you take account of the Earth's motion through the radiation, it is uniform over the sky to about 1 part in 100,000. So it's really pretty uniform. Now, you see, what does that indicate? You say, well, okay, suppose you have a gas in a box, then the temperature would be pretty uniform if it's at the maximum entropy state. You just leave it in the box, and the temperature probably.
So again, this makes no sense when they combine their whole theory, because again, the background radiation was supposed to be radiation left over from the Big Bang. It doesn't make any sense. It's radiation. So frankly, it should be way ahead of us. In terms of where it is, it should be going the other way. It should be going away from us, not into us. There's no way for it to get to us if it happened at the beginning, unless it somehow went faster than the speed of radiation. Yeah. So that's more just, paradoxical mush, blah, 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 blah.
That stuff, it would be uniform temperature. So that also represents high entropy. So where is it low? Well, it's low if you think of not a gas in a box, but suppose you think of a huge box of galactic scale, and it's got stars running around in it. Now those stars will tend to clump because of their gravitational attraction and eventually become black holes. And as they do this, the entropy goes shooting up, particularly with the black holes, because, as we know from Wittgenstein and Hawking, the entropy is absolutely enormous. So that represents an increase in entropy. So you have these two things about the early universe. One is the Planck spectrum, which tells you that the matter and radiation. You see, the Planck spectrum is telling you that the early stage of the universe, photons and matter were kind of maximum randomized as much as they could be, and so that radiation comes to us, and you see this Planck spectrum. But the other feature about it is that it's uniform, and that, as far as gravity is concerned, is very low entropy, because as things start to clump, and a good example of this is our sun. Mm-hmm. See, our sun used to be, a long time ago, a distribution of gas all over the place, and it went through various stages, but it clumped together and produced this hot body. It would be hot even if there were no thermonuclear reactions at all. So it gets that heat, which is, when compared to the darkness of...
So here we go. So the heat thing again, right? So it's obvious as what I've pointed out, is that the Earth is hot in the center because of gravity. The weak force is what's done it. The sun is on fire because of gravity. Continuing.
Background sky is a very low entropy situation. You can get energy out of it by simply...
And we do.
We do, absolutely. That's why we're here. The plants do, by photosynthesis, and we live off plants, and animals that eat plants, and so on. And so that's where it comes from. So it comes from the fact that the sun's a hot spot.
Yeah, it comes from the fact that the sun is a pressure spot. That's where the energy is coming in. It's being pushed into it constantly by the universe. The little cosmic background radiation is really big. In truth, the invisible part of it. And the invisible part of it's going into the sun, and what's coming out later? Photons. That's where the energy came from. Pressure in, pressure out, eventually.
In the cold background sky. And this is why we are interested in the second law of thermodynamics, because it's low and it's creeping up is what we get our structure from and all that stuff.
So ultimately, the cosmic microwave background, it looks like it's maximum entropy, but that's only because you forgot
Exactly.
that there could have been all these lumpinesses, which would have made the entropy much more. I think it's true, the entropy of the black hole at the center of our galaxy is larger than the entire entropy of the cosmic microwave background.
That could well be, yes. And if you look at it, thinking all the stars, all the galaxies that are around, it's absolutely enormous. Like the entropy in the black holes is absolutely stupendous by comparison to anything else.
So this is very good news for the second law of thermodynamics. It explains that the early universe had a low entropy, actually, not a maximum entropy.
That's right.
It's bad news for cosmology because we're stuck with this question of why the early universe is like that.
Exactly.
A lot of cosmologists like the theory of inflation. Proposed.
So again, just more bullshit. If they just had any kind of logical mind, they could figure out that, oh yeah, the stuff is getting all compressed. And when it gets compressed, that means a bunch of energy went in. And then there's less energy out here because a bunch of energy went into the compressed stuff. And then when it starts expanding, then the energy's going back into the field again. The field gets full of energy, and it pushes all the stuff into a little ball again. Wow, that was really hard to figure out. We need 1,000 years to figure that out. Pressure, expansion, contraction, expansion. Ooh, too complicated. Ooh, we need some scientists to figure that out. You know any?
Around 1980, and you were one of the first gadflies there, saying that inflation is a bit of a cheat, I think.
Yes. Well, you see, I thought this is a crazy idea. It won't last a week. How wrong I was. No, I was completely wrong. It just seemed to me such an artificial theory. You had to invent a special field. Well, in the old days they called it a Higgs field because they hoped that the Higgs field would be the same as but that didn't work.
We should explain that the basic idea is that the universe underwent at very, very early times a period of super fast accelerated expansion, which I think you would agree. It's true that if that happened and if the energy driving that expansion turned into matter and radiation, it would give you a universe looking like our universe. But it doesn't help explain the initial conditions.
Yes, it doesn't, because you've got to have it pretty uniform already, otherwise it doesn't even work.
Right.
So it's you can have quite general arguments to show that it can't really be the explanation of the low, not just the low entropy in the early universe, but this particular form that it's low, namely in gravitational degrees of freedom.
Right.
And it does strike me strange why cosmologists, you can see a list of what are the problems of cosmology, and you look down the list and say, where is this?
Yeah, I'm totally on your side there. But so both of us are in the small band.
So it's funny. There's a quote on here, about entropy. From John Carroll. Half of the explanation for the second law is the fact that entropy tends to increase because there are more ways to be high entropy than low entropy. The other half of the question still remains, why was there entropy ever low in the first place? So again, you just can't get the idea that where did the pressure come from to push all the crap that's making up the sun? The pressure didn't come from an infinite vacuum cleaner. It came from a real force, a real pile of energy that had to push the sun together. All the little bits had to be pushed into their locations, and that's where it came from. It came from the fact that it can't go yin until it went yang, and it's just a yin-yang system. It's either compressing or it's expanding. Or it's compressing, or it's expanding. The pressure is either on the outside, increasing on the outside, and decreasing on the inside, or it's either increasing on the inside and decreasing on the outside. And those are the two states the universe can be in. And that explains why quasars are quasars and why galaxies are galaxies. Hello? Can you hear me? No, probably not.
Trying to invent models of the universe which naturally explain this early entropy, but that's where we diverge. So I think that inflation, I would honestly give it a 50% chance of being part of the final answer.
That's a lot more than I'm giving it.
Exactly, but a lot lower than all my friends give it, right?
Oh,
As
absolutely,
professional
yes,
cosmologists.
right.
So,
Yes.
and you've been working very recently on a new model of the universe on its super largest scales.
That's right. Well, recently isn't even all that recently. It's I forget now.
Well, I mean, inflation is this silly idea that the universe expanded faster than the speed of light, which is just, what a waste of fucking time. So, what the hell? Why should... That's moving Red Riding Hood into Goldilocks' house. You know, and they're both like crack whores with 5 kids. 5 kids with 7 vaginas.
Over 10 years anyway.
Okay.
But nobody paid. Well, you see, it took me a long time to... I used to lecture about... Let me explain the model first.
Please.
The argument is that, think of the two ends of the universe. We have this future which seems to be dominated by this exponential expansion. So this is observations of supernova stars and other things together, which persuaded cosmologists not to give the two groups the Nobel Prize, which was very deserved, to see that the universe is having this, what's called an exponential expansion. It's a sort of self-similar. The rate of expansion is proportional to the size. So it's something which seems to be taking place. Now, those of us who were brought up on cosmology and read the cosmology books would have seen that these...
I thought he was going to say brought up on crack. Yeah, methamphetamine and stuff. Because, yes, you obviously weren't fed milk and toast. There was some lead in it somewhere, in my opinion.
Also, that exponential expansion are perfectly well described in the books. These are models in which there is a thing called the cosmological constant, which is positive. And it's usually referred to as a lambda. Capital lambda is just like a V upside down.
Right, basically the energy of empty space.
Well, you can think of it as energy. People call it dark energy, yes, right. Yes. I'm not sure I'm happy with that term, but never mind. That's it's certainly well explained by this Einstein cosmological constant. Einstein introduced this term in 1917 for what was the wrong reason. He wanted a model which was static. He hoped that the universe was static. I think it's a sort of appealing idea. The steady state model is again the same sort of appeal, philosophically appealing in some way.
To be fair, I think it was also the observations at the time. The universe looked static to astronomers in 1917.
I guess Hubble hadn't quite...
Right, that was 1920s.
It was after... I can't remember. It was after the Vesto-Slipher, wasn't it? When Vesto-Slipher had already seen the expansion. Maybe it wasn't such a convincing argument.
Well, you saw that there were objects that were moving away from us.
Yes.
So again, we don't see them moving away from us. We don't see them getting smaller and smaller and smaller. We don't see any of that. We just see redshift. And the redshift can be understood to be a consequence of something other than movement away, because the light is traveling billions of miles. And there could be other things to account for the fact that it gets redshifted traveling billions of miles. And as I pointed out, all it has to do is hit a few little transparent atoms, hit a few hydrogen atoms on the way, and the hydrogen atoms are coming towards it, and it hits them. Then when as the hydrogen atom moves away from the location where the photon hit it, it will automatically redshift the photon a little bit. There, redshift explained. No, you don't need a complex explanation. You don't need to leave it unanswered. You don't need to freaking cause the whole universe to be doing some retarded expansion bullshit, everything moving away from everything as if there's no middle at all. Things don't explode that way. We see rings in the universe because things explode radially. They don't explode by everything moving away from everything else. So, just crap. Crappy.
They were far away.
I guess that's true. It probably wasn't terribly persuasive, but there was some indication, but not enough to rule out a model like Einstein, the one he produced then. But for that model, he needed this term. And it's the only thing you can really do to Einstein's equations without wrecking them, in my view. Mm-hmm. You just add this term, and he didn't like to do this at first, but I guess he thought, well, let's put it in, and then you get a static model, which we refer to as Einstein cosmology. But then, not long after that, Hubble showed pretty convincingly that there was this expansion in proportion to the distance, so the whole universe seemed to be taking part in this expansion. And so Einstein, I guess, kicking himself for not having stuck to his original equations, which seemed to indicate he would have
So
predicted it.
He could have become famous, yeah.
Yeah, he could have become famous, yes. Well, he considered this to be his greatest blunder. And I think that's true. It's on record. I think Gamow has recorded Einstein having said this. So, okay, this is... but it's all in the cosmology books, despite Einstein sort of retracting it. And yeah, people studied it. I studied it. I looked to see what the infinity looked like in this model and so on. So I was familiar with it. Although I was a bit slow on the uptake to taking it seriously. I think it was Jerry Ostreicher who told me. I said, well, maybe these distant supernovae look red because of dust and so on, which people thought maybe was the case. And he said, oh no, there are all sorts of other things. It's not just that. You have to take it seriously. So I thought, okay, I'll take it seriously. And it wasn't, I don't know how long after that conversation, that I began to think about the remote future. Now you see, the remote future, and I mean the very remote future, we have the universe expands and expands and expands, and it gets more and more rarefied, and nothing much happens. You get sort of dead stars, and it gets pretty boring. And the most exciting things are around these black holes. But they're pretty boring.
Yes, I'm having that boring part. I must have fallen into the part of the multiverse that's insanely boring. Oh, God, amazing. In this conversation, they would say the word boring. It's just so obvious. It's like, I don't know, nipple on an Australian beach or something. It's just so obvious.
Around waiting for it to evaporate, according to Hawking's evaporation. And for the big ones, it takes about a googol years, something like that. So you're thinking about 10 to the 100 years, 1 with 100 zeros, that number of years. Yes, and that's an awful long time. So I regard that as a pretty boring area. We'll wait for that. But then you see, after it's gone off pop by Hawking evaporation, no, that's the very boring era.
Not even black holes. Yeah.
That's right. I mean, I couldn't think of anything more boring than that. And I admit this is an emotional argument, but it just seemed to me, for our universe, that's it, you see.
Horny.
It's forever and ever.
I'm horny.
Eternal tedium, you see.
Well, it is weird, and I think that cosmologists underemphasize how weird it is. We
Yes.
always talk about the last 14 billion years of the history of the universe, because that's the past, that's what we've observed, and we
Yes.
say it's a long time and so forth, but our best current models say we have infinity years toward the future,
That's
which
right.
is a rather big imbalance.
And interminable
Yeah.
boredom, yes. Well, you see, then I began
All
to
right, they
think,
keep saying the word boredom like people are going to be realizing, oh yeah, I'm getting that. Oh fuck, I thought I was saying, what am I feeling? Oh, that's right, it's boredom. Holy shit, I'm bored. Lion picture. First lesson of love is to learn how to be alone. Yes, learn how to. You really do just have to. Just first lesson is don't step in glue. It's sticky. There, that's the first lesson in life. Don't step in glue. It's sticky. It's a trap. A glue trap. Love is a glue trap. There, that's your first lesson.
who's going to be around to be bored by this? And I thought, well, pretty well photons. And it's damn hard to bore a photon. That's actually, I don't expect it to have actual experiences, so boring is perhaps not an appropriate term.
Again, to be fair, I did interview David Chalmers on the podcast, and he thinks that photons can have actual experiences. Just a little bit. So maybe, let's think about the photon's feelings here. Let's take those into account.
Okay, well, that's
Oh
actually,
yeah, it's just such. Let's reveal our real religious selves and start talking all kinds of silly wooey stuff. Lovey, feely, fuzzy.
because they still don't get bored. They don't get bored because if you take relativity, now this is ordinary old-fashioned special relativity without the curved space-time and all that, doesn't matter curved or not. The photon, because it travels at the speed of light, the time is just stretched out and it's nothing. So right from its creation in some particle decay or something, this photon goes out to infinity and it experiences zero time. So it's not bored in the sense of forget about whether it actually has feelings or not. It doesn't experience the passage of time. Now this is the sort of thing I used to play around with when thinking about gravitational radiation and how
It's just kind of silly. It doesn't experience. Yes, of course, it doesn't experience anything. So yes, it can't experience time, but it endures it. So I think it's just silly to think the photon doesn't go from here to there, and in a sense, the universe it's passing a world that's changing. Now, yes, maybe the photon has no windows and it can't look outside and see that the universe is flying by, but that's the truth. The truth is changing its position is a real event. It's not a non-event. It endures the event until it finally hits something. But it's not, to say it's instantaneous to the photon is retarded because the photon can't experience time. But the simple truth is it does take time. Photons don't do anything instantaneously. Like everything else in the universe, they have to wait for it. These aren't complex philosophical points.
On space-times and so on. And it was a useful way to think that this boundary is something you could imagine going through, and if you were a massless thing, when you hit that boundary, you say, well, where the hell am I? You see, there's got to be something on the other side, you might think. I mean, it's only a way of thinking. I didn't think of it seriously that way.
So, let's just, I think, just to get this correct in people's minds, this is a boundary.
Yes, let's get it correct in people's minds. I've come on a podcast, and I'm not right now, just, we're neck deep in just bullshit conversation. And he just admitted it. This isn't stuff I take seriously. This is just bullshitting. So, what's I guess I can do that. I can just, let's see who can make up the funniest story about where this was 4 years ago. I think it's a pedophile. Look at it. It looks like a pedophile. It was molesting a child, for fuck's sake. I could do that. But it would be some kind of rational point in just making shit up.
About is literally infinitely far away, but you're saying the photon experiences 0 time, so it gets there.
That's exactly right. But I think it's very useful if you have seen these pictures by the Dutch artist M.C. Escher. There's a very famous one with angels and devils, and they, in the middle you can see the angels and devils interlocking, and then you go out, there's a circular boundary, and they seem to get smaller and smaller and smaller, and they crowd in on that boundary. Now, this is a representation of a kind of geometry, which is called a hyperbolic geometry. And if you think of those angels as really all being the same size as each other, and the devils all the same size, then although it looks to us as though they get smaller and smaller, to them, they're all the same size.
And did you have something to do with inspiring that Escher?
No, that was my relation to Escher was something a little different. But that was Coxeter. It was the same meeting. Yes, this was in the International Congress of Mathematicians in whenever it was, early 50s, I think. And it was the mathematician Coxeter who wrote to Escher and said, well, you might find this interesting to explore. You see. So no, that was amazing.
So it's a representation. It's in the spirit of what you did for Spacetime and General Relativity,
yes.
Where you can express.
Oh, fuck. Okay, so I think we're done, right? We're out of pictures. I could play with the transparency a little bit. Just make it much more transparent. Yeah, so this is probably enough. I mean, a little more than halfway through. Maybe I'll come back to this, but is there any real point? It's just make up bullshit. That's all it is. Let's just make up bullshit. So anyway, turtles. Did you see the turtles? Yeah, that was really cool. Oh, the turtles aren't there anymore. Damn fucking universe is always changing things. Damn entropy. Alright, so anyway, this is, I thought it would be stupid, and it's just so much more stupid than I thought it would be. So I thought I could make some kind of physics out of this, but there really just isn't any real physics. Just a bunch of wooey bullshit. It's just another religion. It's just they could just be talking Scientology and you get that power feeling like confidence does so much for you. You feel like if you feel like you're a surgeon, you can be a surgeon. If you feel like you can do it, you can do it. Power of positive thinking is really powerful. Yeah, and it also creates a ton of failure. A bunch of people thinking, these people think they can do physics. I have a degree, I can do physics. Well, apparently you can't. Worse shit, you keep getting every single question wrong. Plus, minus. Minus, plus. Oh, wrong answer. Push, pull. Pull! Wrong answer. I mean, it just goes on and on and on and on. Wrong. Galaxy's getting bigger. No! Smaller! Wrong answer. Yeah. Every single question. Wrong answer. Alright. what do I have to do now? Oh, hopefully the file will save. Oh, wouldn't it be a terrible tragedy if we lost this frickin' video? Oh.